Dynamic partition scheduling of real-time DAG tasks on ARM big.LITT architectures. Nowadays, we have more and more multiprocessor devices and more coming in the future, leading, for example, Android running smartphones and smartwatches. Users require interactive contents and applications, demanding high quality and responsiveness, which leads to the need for real-time capabilities of such systems. A fundamental problem in real-time scheduling is the task partitioning, where we want to assign a new task, in this case DAG task, to a set of cores, while trying, for instance, to minimize the device consumption or having the best performance possible. But to assign a DAG task to a set of cores and save energy, it is important to have an effective partitioning strategy. In this paper, we consider a system where many soft real-time tasks can be concurrently active on the same CPU and interfere with each other, jeopardizing their deadlines. Therefore, we make use of resource reservations to enforce temporal isolation among tasks. Also, we make use of the constant bandwidth server, CBS for short, as a resource reservation mechanism, grouping a set of nodes of the same DAG task. A CBS server is associated with two parameters, the budget and the reservation period. While a reservation is scheduled, its budget is decreased accordingly, and if a task tries to execute more than its budget, the server deadline is postponed by its period. On a core, there might be many CBS servers, and so a core schedulability condition is, in the case of EDF, the sum of all the servers' utilization less or equal than 1. An energy-aware extension of the CBS server is grab-PA, which means greedy reclamation of a used bandwidth power-aware, integrating the ability to reclaim unused processor capacity and exploiting the hardware DVFS capabilities to reduce the core's frequency and energy consumption. grab-PA has been implemented in the mainline Linux running shed deadline CBS reservations from version 3.14. grab-PA behavior could be summarized as follows. When a new task instance arrives, the first free core is selected if it is available. Otherwise, the core with the latest deadline task is chosen and the new task is dispatched onto it. Then, in the case of ARM big.LITT, the highest utilization core of each island is used to determine the frequency, or the highest frequency is chosen if the busiest core has utilization greater than 1. When a task in a server ends, leaving its core idle, the task with closest deadline is pulled onto it and the island frequencies are adjusted. In the literature, there are not many approaches available for scheduling real-time DAG tasks on our big.LITT architectures to reduce the energy consumption. About the works dealing with scheduling sequential tasks in an energy-aware way, some approaches make use of linear programming to achieve the optimal solution, while others consider heuristics and the DVFS. We have explored this problem in a previous work, and since this approach that we used is central in this paper, it is deeply explained later. About the works dealing with scheduling sequential tasks in a thermal-aware way, some approaches achieve the optimal solution via ILP. Other ones try to minimize the peak temperature and to make the cores go idle as much as possible. And finally, other approaches make choices based on the past data in a feedback loop-based way. Until here, the literature about sequential task scheduling has been summarized. About the state-of-the-art approaches for DAG scheduling, some try to do it in an energy-aware way, while others don't. As for the non-energy-aware DAG scheduling, some works only consider analysis and schedulability issues. Other ones explore partitioning techniques based on semi-federated and federated scheduling. And finally, some works use the gang scheduling, in which all parallel instances of the same task start and stop on the processors at the same time. As for the energy-aware DAG scheduling, there is not much in the literature, and we base the solution of this work on a previous work of this field, exploiting and refining its task decompositioning technique. Since this approach is central in this paper, it is deeply explained later. Notice that the previous solution is based on the concept of speed profiles, which, given a DAG task, provides the time percentage needed by the task for each speed available on the platform, and this is used to identify an energy-efficient core-to-task mapping, while our approach is based on the core utilizations. In this paper, we consider an ARM big.LITT architecture in which the big island has maximum capacity 1 and the little island has maximum capacity 0.34 as in the Odroid XU3. The power model that we use is tuned on the Odroid XU3 and tries to be a compromise between representativeness and complexity. Power consumption depends on both the voltage and the frequency, and on the task workload type, and does not consider interference due to other tasks and path, cache, and memory contention. Also, we consider a set of n soft real-time DAG tasks with implicit deadline, which means that the period is the same as the deadline, and each DAG task contains a set of nodes with associated nominal vset, where nominal means that it is referred to the big island when running at maximum speed. We consider an open and dynamic system where the user launches and closes application without a fixed initial plan. The problem tackled in this paper is the scheduling of a set of DAG tasks on ARM big.LITT architectures for energy awareness. So, given a DAG like the one in figure, representing for example a real-time video game or an audio pipeline with each node associated to an audio filter, we need to split its nodes into groups represented in the image by different colors. And finally, we want to place these groups of nodes, which are transparently turned into CBS servers, into the available cores to achieve the lowest energy consumptions while guaranteeing deadlines. In the figure, the CBS servers are placed onto the available cores of the considered ARM big.LITT platform, and the cores have different loads. The core with highest load determines the island frequency, which we want to be as low as possible to minimize the energy consumptions. We now present our solution. When a DAG task wakes up, we need to split its nodes into groups of CBS servers, and then we need to partition the servers into the available CPUs in an energy-aware way, respecting the DAG task soft deadline. To split the DAG into groups of CBS servers, we use the task decompositioning technique presented in the literature, and we refine it to make it work properly with our partitioning technique. In fact, since the original technique was used together with the concept of speed profile, as explained before, we refined it to decrease the CBS servers utilization as much as possible, and we achieved this goal by changing some of the phases on the original technique. Once we get the set of CBS servers for the DAG task, we need to place them into the available cores. Our partitioning technique is an extension of a previous work of ours to the case of DAG tasks, and it works transparently, without the need to modify any application at user level. The partitioning technique decides core and frequency for each of the CBS server and provides the heuristically best core given the minimum additional power consumption. Given a CBS server, the technique loops over all cores and their frequencies, starting with the same island where the task is already located, keeping its current frequency if possible. The first check is that a job that do not miss their deadline and they are schedulable with EDF. Then it computes the difference between the power consumption due to the current core assignment with the one of an alternative assignment to a different core, considering the possible impact on frequency scaling. Power consumption is calculated based on the island and utilization of the new task. When the loop is over, the core with minimum additional power consumption is chosen. As mentioned before, we want the CBS server's utilization to be as small as possible, because this makes the core's utilization smaller, and this translates to lower frequencies and less energy consumption. The reduction of the utilization of the CBS servers is achieved by refining the original task decomposition technique, which is applied only one time per DAG task. The phases are as follows. In the first phase, the input DAG task nodes are decomposed into groups of nodes, and for each node, the arrival and finishing time of the first distance is determined. In the example of the DAG with deadline 50 time units, the nodes N3 and N7 in violet form a group, which is practically a CBS server, and N3 is assigned initial arrival time 15 and finishing time 17, while N7 is assigned initial arrival time 17 and finishing time 21. We also notice that there is some slack time equal to 50 minus 39 and highlighted with a circle in the bottom right corner. We will use this in the next phase. The second phase uses the slack time as found in the previous image to relax the node's initial finishing time and thus decrease the CBS utilization. The slack time is allocated uniformly among the nodes. Since the critical path of the DAG task is long 39 time units and the DAG deadline is 50, we can multiply the node's initial finishing time by a factor of 1.28, relaxing, for example, the finishing time of N11 from 39 to 50. In the third phase, we perform the segment extension. The absolute final time computed at the previous step is too strict for the nodes without successors, and thus it can be further extended, which contributes to the reduction of the server's utilization. For example, N9 has no reason to finish at time 40, as obtained in the previous phase, and since it only precedes N11, its initial final time can be extended to 48, which is the initial arrival time of N11. In the last phase, we relax the finishing times, distributing the time window of each server to its nodes, proportionally to their nominal vset. This is the last effort to reduce the server's utilizations. For example, the server containing N3 and N7 has a time window of 11 time units and a total vset of 6. The ratio between these two numbers is 1.83, which can be used to relax the initial finishing time of both nodes, and the one of N3 increases to 22 and the one of N7 to 32. This makes the resulting CBS server reduce its utilization. We evaluated the proposed approach called big.LCBS with the state-of-the-art graph PA on randomly generated task sets of 1, 2, and 3 DAG tasks with a total of 24 nodes, and with DAG utilization from 0.2 to 0.7. To represent a more dynamic environment, the execution time of the nodes instances is said to be uniformly distributed between 0.1 millisecond and the node nominal vset. Moreover, we parameterized its server with a budget equal to the sum of the nominal vsets of its nodes and period equal to the time window as found during the DAG decomposition phase. Since all the servers of the DAG are dispatched onto cores at the beginning of the DAG period itself, cores have been assigned an overprovisioning factor of 0.8. Results are promising. In these graphs, we see on the left the average energy consumption for increasing DAG utilization, and on the right the same data in a hyperpolated independent way. As we can see from the left, BLCBS in green always consumes less than GRAPH-PA in black and GADF. And this is because BLCBS always chooses the core with minimum power increase and tries not to raise the island frequency when possible, while GRAPH-PA chooses the core with latest deadline and, like GADF, does not care about the consequent frequency increases. Moreover, GRAPH-PA consumes less than GEDF because the latter, GADF, keeps the highest frequency throughout the simulations. We now increase the number of DAG tasks to 2, each with 12 nodes. Again, BLCBS consumes less than GRAPH-PA, and as we can see on the right, the ratio between the energy consumption consumed by GRAPH-PA and BLCBS in green tends to 1 in average over all the considered DAG utilization. BLCBS still consumes much less than GEDF, as in black, which keeps the highest island frequencies for the entire simulation. When we have 3 DAGs with 8 nodes each, again BLCBS consumes less than GRAPH-PA and much less than GADF. We notice that with respect to the case of 1 DAG with 24 nodes, in which consumptions reach 90 millijoule, here it is 4,000 times higher. Now we consider the frequencies for both BLCBS in green and GRAPH-PA in black, for the little island on the left and the big island on the right. For the case of 1 DAG with 24 nodes, BLCBS uses lower frequencies than GRAPH-PA on both islands. When considering 2 DAGs with 12 nodes, BLCBS keeps using frequencies lower than GRAPH-PA on both islands. We also notice that the average frequencies grows with growing DAG nominal utilization on both islands. The same behaviors are shown for 3 DAGs with 8 nodes each. Considering BLCBS in green, the little island frequencies on the left are higher than the one of the big island on the right. In other words, we avoid increasing even more the big island frequency, and we are happy with this behavior because the little island is thought for energy saving. The same thing holds for GRAPH-PA. In conclusion, in this paper we incorporate DAG placement and splitting strategies to reduce the energy consumption. We extend BLCBS to support DAG tasks and open and dynamic scenarios, reflecting typical Android use cases when running on the big.LITT architecture. Experimental results on random task sets show that our technique achieves an average of 10% energy saving with respect to the state-of-the-art GRAPH-PA. As for the future works, we plan to improve the performance of the placement algorithm and to place the servers on the cores, also considering other factors, like the nodes relationship and the memory energy consumption and different workload types. Also, we can consider the CPU deep idle states, and we can incorporate the bandwidth reclaiming and feedback mechanisms. Thank you.